My presentation is going to be on Hawking radiation. So the main points I want to go over in this presentation are the two related constituents to Hawking radiation, which are virtual particles and black holes. Then we will get into Hawking radiation as it was derived by Hawking himself, and then its relation to thermal and statistical physics. To begin, we need to talk about what virtual particles are. So virtual particles come into effect because quantum fields can never be perfectly zero energy, because over some finite amount of time, because they are energy and time are a conjugate pair, they are subject to the Heisenberg uncertainty principle. And so in some finite amount of time, there is always a chance that a particle will pop up to an energy level within the quantized levels that will give you a particle. Now, because of conservation laws, that also means that a virtual antiparticle needs to be made to keep the energies equivalent. And these will exist for a short time, and then they will just cancel each other out. And what you have is, for a shorter time, you can have higher energy particles. So, like, if this particle was way up in the quantized fields, it would be around for a much shorter amount of time. And black holes are a region of space where gravity is so strong that no particle or even electromagnetic radiation like light can escape. So nothing can escape a black hole's hole once you cross the event horizon, which is just the very edge of the black hole. And these are caused when mass becomes so extremely densely packed that the gravitational force is so strong that it even pulls light in. So now we can talk about Hawking radiation, and there's multiple theories as to the origin of Hawking radiation, and they all come out to the same idea, but because we don't have a generalized theory of relativity and quantum mechanics together, scientists kind of have to do weird kind of workarounds to try and couple them, and so there's different ways to all get to the same point, so we're just going to look at the way Hawking derived it. So to begin, you start with what is called a null geodesic, which just means you start from a point in time that goes from an infinite past to an infinite future. And your particle is just kind of traveling through this null geodesic in a trajectory. And what happens is, in this situation, what we have is that the particle is the very last trajectory to travel through before the black hole is formed. And so what happens is you kind of get these distortions in the uh, quantum field that will eventually lead to our Hawking radiation. Now, because what we're looking at here is more of a general relativity view, Hawking needed a way to combine quantum mechanics to this, and so he had to use what were called the Bogoliubov transformations, which are these transformations right here, that basically allow you to kind of take a Hamiltonian operator and put it and transform it between the two. And what we see with this distortion then is that what we call the forward moving frequencies, or just the normal matter that are moving regularly through time, are going to be distorted into the future, which is us, and so those are the particles that we are going to see. Is we're going to see these real particles be ejected out of the black hole, and it looks like it's just kind of radiating from it. We do also have that on this side, the blue represents the antimatter pair that would go along with it, and you'll see that it's actually kind of jetted back into the past, almost. And so the radiation that results, we actually see that because of the math of these distortions, that it's actually going to be the de Broglie wavelength of this radiation is actually going to be proportional to the radius. So a very big black hole is going to give off less energetic and longer wavelength particles. This is why when black holes are larger, they radiate less, and so they actually lose mass slower. And then as their radius goes down, they will start ejecting energy faster and die out. And the temperature of the radiation that's given off is given by this equation here. And one of the interesting things in the first relations we see of this to thermodynamics is that the frequency of this Hawking radiation, if you were to match like the frequencies coming off, would look like the frequencies of the radiation of like a black body that we saw if you in like modern physics. And so now we can talk about black hole thermodynamics, and first we can look at what was kind of around pre-Hawking radiation, and then we can see how the Hawking radiation allowed us to get a good idea of the entropy of a black hole. So to start, we basically have the 3 laws of thermodynamics plus the 0th law, and they all kind of have analogies from the regular thermodynamic laws to the black hole thermodynamic laws. So the first one we see is that the surface gravity of a black hole denoted k, which the surface gravity is basically the acceleration you would feel like right at the event horizon, and it is constant over the horizon of a stationary black hole. So this is kind of analogous to like temperature, because we say that like in a thermal equilibrium, all the temperature is the same throughout. So this is kind of like the stationary black hole is kind of like your thermal equilibrium. Then, just as we have the first law of thermodynamics gives us an equation for the change in energy, we also have a similar equation for black hole thermodynamics. So this tells us that this is your change in energy. This term that uses the surface gravity as well as dA, we will see contributes to your change in Q term that you would normally, your Q term that you would normally see over here, because Q is temperature times your change in entropy. And so it'll eventually be shown that we already have K here is analogous to temperature, and so we can show that the dA is kind of analogous to your change in entropy. And then these terms over here relate to basically the work done on the black hole. For instance, J is your angular momentum, Q is kind of your charge of the black hole, and then we have here the angular velocity and the electric potential of it. And these two terms together are basically equating to your work of the black hole. So next we have the second law of black hole thermodynamics that says the horizon area can never decrease over time. And so as I said previously, that kind of shows us that like the horizon area here is sort of like entropy, because entropy can also not decrease over time, and so it's kind of analogous that your horizon area is similar to your entropy. And then the final one we have is just that the surface gravity k cannot go to 0, and that basically has to do with this term here, that like if k starts going to 0, then your entropy is going to go to 0 as well. So now that we have Hawking radiation, what we can see is we can rewrite the Hawking temperature using the surface gravity k as this. And so what we'll see is if we go back, if we say that if we have a term here that is temperature, temperature is not directly equal to k. It's actually related to it via this equation. And so if we put the Hawking temperature in here, and then kind of say like that the Hawking temperature times ds, and relate it to this k term and your s and your ds, what you'll get is that the entropy of a black hole can be written as the horizon area over 4h bar g, where this is your universal gravitational constant.